Hey everybody, it's me. So this is going to be the last video of this lecture and the last thing that we're going to do before the second exam. Now this problem, it takes a lot of work. It sort of brings together everything that we've talked about in terms of exponential equations, solving exponential equations using logarithms, and there's a lot of algebraic manipulation in here. So I recommend, if you're near the bottom of a piece of paper and you're taking notes, to start on a new fresh piece of paper. So suppose that the carrying capacity M of the human population on Earth is 35 billion. In 1987, the world population was about 5 billion. We want to use this logistic growth model to calculate the average rate K of growth of the population, given the population was about 6 billion in 2003. So logistic growth, it's similar to exponential growth. So it starts the same way. You get this curve. But what happens is, with logistic growth, it takes into account that there are resources. There's a finite number of resources out there. And so then the curve stops growing exponentially and starts curving back down, approaching some carrying capacity. And in this case, that carrying capacity, M, is 35 billion. So let's say we're here on the curve. Eventually 35 billion, if this model is correct, would be where we top out. Okay. So in order to answer any of the questions about this particular problem, we would need to find A and we need to find K. And so the problem on your problem set, not only do you have to find A and K, but then you have to answer questions about it, similar to how we did back in when we were talking about exponential growth or the McDonald's cooling problem, that kind of stuff. So we're going to start by finding A. So right now we know that the population model that we're looking to find is 35. I'm just putting this in for M. And again, P of t is going to be in billions here, so we don't have to write 35 with 9 zeros after it. And then 1 plus a e to the negative kt. Now we know that originally, meaning when the population, meaning that t equals 0, so we're going to say t equals 0 is the year 1987. So that means in the year 1987, which is when t is 0, we had a population of 5 billion. Okay. So I'm going to do a little bit of voodoo here called algebra. I'm going to multiply both sides by the denominator here, and I'm going to divide both sides of the equation by 5. And that is the old switcheroo, okay? We're basically just switching these around. And so I get 1 plus a. And I just get a because 0 times k is 0, and then e to the 0 is 1. So this term right here disappears and becomes 1. And that's why I need that initial date. So we're setting t equals 0 to be 1987, so we can get rid of that e term. And so that means that 7 equals 1 plus a. So a is equal to 6. So now that we know that a equals 6, we have that p of t is 35 over 1 plus 6 e to the negative kt. So now we need another piece of information in order to find this k value, which is actually what we're looking for. Well, luckily, in the problem, it says that the population was about 6 billion in 2003. So compared to 1987, if that's when t equals 0, how many years later is 2003? Yeah, 16, right? So that means P of 16, which we know is 6 billion, is equal to 35 over 1 plus 6e to the negative k times 16. So now my goal is to solve for k, but I'm going to do that same switcheroo trick. I'm multiplying both sides. It's not a trick. I'm just multiplying both sides by this, which gets rid of the denominator over here and puts it on this side of the equation. And then I'm going to divide both sides by 6, which gets rid of the 6 here and puts it down where that one was. So that means that 1 plus 6e to the negative 16k is equal to 35 over 6. Now 35 is not evenly divisible by 6. So we're going to leave it 35/6. Now I'm going to subtract 1 from both sides. I'm trying to get everything away from this term so that I can eventually get to k. So let's subtract 1 from both sides. But when I subtract it from the other side, I'm going to make it a fancy one. 35/6 minus 6/6. Okay? So that gives me 6e to the negative 16k equals 29/6. And again, 29/6 cannot be reduced. 29 is a prime number, so. But I still want to get this by itself. So I got to get rid of the 6. So I'm going to divide both sides by 6. So e to the negative 16k is going to be equal to 29 over 36. If I divide by 6, then this 6 gets multiplied by another 6, which gives me 36. And now I'm at the point where I can use my knowledge of logarithms to rewrite this as a log. Because I got to get at this exponent, so I need to use logarithms. It's the only way. So I can either ln both sides, which some people are comfortable with, or I can use the definition of a logarithm and just rewrite everything where it goes. In this case, the base is e, so log base e of 29 over 36 is going to be equal to negative 16k. So you can write log base e, but you should really be writing ln. And then to get k totally by itself, k is going to be ln of 29 over 36 divided by negative 16. And now that we have the exact answer to infinitely many decimal places, if we really want to, we can convert this to a decimal to put it back into the equation. I'm just typing it into my calculating machine here. And so that gives me 0.0135139, okay? So going back to the original equation, P of t is 35 over 1 plus 6 e to the negative 0.0135 t. And now that I know all those different parameters of my equation, I can answer any question now. If they said, well, what will the population of the Earth be in the year 2020? Well, I could plug 33 in for t, and I could find the population. Or if they asked, what year would the population be 10 billion? I can put 10 in for P of t, and I can go through this whole process that I just went through here, but instead of solving for k, you'll be solving for t. So you'd be solving for t, which is exactly the same as what we did here to solve for k. It's the same exact process. They might also ask the question, what is the maximum population of the Earth? And we knew that without doing anything. It's 35 billion. That's what it is. Okay. So you have all those tools at your disposal, and you can go ahead. Actually, if you want, I can go through finding. So P of t is 35 over 1 plus 6e to the negative 0.0135t. We want to know when the population is going to be 10 billion. So first I do the old switcheroo. Now I'm going to subtract 1 from both sides. So we have 35 over 10 minus 10 over 10. That's 6e to the negative 0.0135t. So that gives me 25 over 10 equals 6e to the negative 0.0135t. Then I can also divide by 6, which gives me 25 over 60. That can definitely be reduced. Divide by 5, right? So that's 5 over 12 equals e to the negative 0.0135t. I need to get at this exponent now, so I'm going to ln both sides or rewrite it as a logarithm. Either way, I'm going to get that negative 0.0135t is equal to ln of 5/12, which means that t is equal to ln of 5/12 divided by negative 0.0135. And I'm just interested to see what year the population is going to be 10 billion. According to this model, this is not necessarily accurate. So that says 64.8. So 64 years after 1987 is 2051 is what it's saying. In the year 2051, the population will be 10 billion. I have a feeling it's going to happen before that, but whatever. So there you have it. Watch these lecture notes again if you need to, and do the problem sets on Pearson. Also do the study guide, study plan questions that are in the prerequisite tab. Thank you, and please email me if you have any questions.